Hi, everyone. We're very excited to present I'm very excited to present the next speaker. He is one of the two inaugural winners of our new award, so the CHCCS Graphics Interface Award for Early Career Researchers. So I'd like to just talk to you about this award for a minute. It is meant to recognize, support, and encourage outstanding early career faculty members in the fields related to graphics interface conference. So that covers all aspects of graphics, HCI, and visualization. The award is meant to be given annually to up to 2 individuals and presented at the conference. And we had many great applications this year, which was fantastic for our first instance. And so one of our 2 winners is David Levin, who is a Canada Research Chair in Simulation-Driven Graphics and Fabrication and an assistant professor at the University of Toronto. When we looked at his application, it was obvious that he was a leader in graphics research, sustained a record of high-quality, high-impact research on the topics that are core to computer graphics, specifically numerical simulation for fabrication and animation. And the value of his work was clear from the adoption of his techniques in real-world films and game applications. He exemplifies the goal and missions of GI. So it's really fantastic that he gets to present his research to all of you today. David, the floor is yours.
Great, thanks, Audrey. Thanks for that great introduction. Hopefully everyone can hear me and see me. So I really couldn't be more pleased to be invited to talk at Graphics Interface.
Apologies to interject. We see the presenter view on the screen share.
Oh no, my notes, my precious, precious notes. Now I'll have to come up with a whole bunch of new jokes. Is that showing the slides now?
Yes, now it's perfect.
Perfect. Okay, I'll skip that part. So yeah, I mean, despite the fact that I had to write it down, I really am thrilled to be here at Graphics Interface 2021. And it's a huge honor to be awarded one of these inaugural Early Career Research Awards by the CHCCS. And I just really love getting to talk about 2 of my favorite things, which are physics and computer graphics. But before I do that, I want to start by thanking all my amazing friends and colleagues and collaborators, students, for getting me here to this point in apparently what is still my earlier career. At 41, I'm probably the oldest early career researcher ever. So there's really like a lot of people on this list. And you know, I'm very cognizant of the fact that I'm a product of my environment, and I've been very lucky to always find myself in environments that are supportive and inspiring. So this has really been the case for all stages of my career so far. So from my time working at Forward Imaging, which was a medical imaging startup in London, Ontario, to my master's in biophysics at Western University, all the way through to my PhD at UBC and my postdoc at MIT. And I want to just pause here and say like a huge thank you to Dinesh Pai, who was and continues to be just a phenomenal teacher and mentor. You know, it was Dinesh's willingness to take a risk on me as a PhD student to let me come switch fields to graphics, and his guidance over the course of my degree really like put me on the road to much of the success that I've enjoyed ever since. And of course, none of what I'm going to talk about today would be possible without my amazing graduate students. These are the students that I directly supervise, but really everyone back at the DGEP deserves a little bit of recognition. If I could break up the award Mean Girls style and give it to each and every one of you, I would. And finally, I want to thank my family, including my super talented partner, Maria Shagrina, my daughter, Yana, and our 2 cats, Seema and Tanya. Maria won the Alan Fournier Prize this year. So if you missed her talk, you should definitely go and check it out on the GI YouTube channel. But before you run off and do that, hopefully you can stick around for a little bit, because you know, I want to tell you a story. And this story starts way, way back in 2006. Just to set the scene, the critical darling, the Fast and Furious Tokyo Drift, raced to number 41 at the box office. And I was working on building real-time surgical simulations for prostate brachytherapy. And if you don't know what that is, definitely don't look it up on the internet right now. More or less, this involves doing 2D simulations of poking people with needles. And the algorithm that we had come up with was this funny thing that did mass spring simulation because it was very fast. And then it kind of iteratively visited each spring and applied some constraints to limit their deformation. It worked pretty well, but it was sort of chock full of hyperparameters, which I, as the student, had to manually tune. And more out of frustration than anything, I wrote this in the paper, that a physically based model with meaningful material parameters could have saved me all of this time. And while I was trying to figure out how to make this more physically based, I stumbled across this paper by Doug James, Dinesh's former PhD student, now Stanford University professor. And this kind of blew my mind. This was an amazing real-time physics simulation. It wasn't coming out of numerical methods or the engineering community, but from computer graphics. So I saw this and I thought, look, this is where I need to be. This is what I need to do. And I applied to work with Dinesh, and then the rest is basically history. And so at the University of British Columbia, I got introduced to the field that essentially has defined my career up to this point, which is physics-based animation. And when I arrived, I was a neophyte. And so in order to try and catch up a bit, I went looking through old literature. And that led me to this paper from 1987. This paper by Dimitri Terzopoulos really introduces physics-based animation to the field of computer graphics. And it looks pretty good, actually. They simulate cloth, they simulate volumetric objects, they do collisions using penalties. It's actually a really, really impressive paper. And if you're at all interested, you should really go in and read it, because it sets the stage for still what is like a lot of the modern techniques that we use in the field. But what caught my eye most was in the text. Terzopoulos points out that active models, their name for dynamic physics-driven models, could potentially produce realistic, diverse interactions simply by implementing the rules of physics. In other words, we could be free from hand coding or hand animating every possible interaction between objects in a virtual world. The correct behavior would just emerge from the physics. And for me, this resonated. I had been in the trenches hand tuning parameters to try and match a real world result. And it was awful. The power of physics simulation and animation was that this complex behavior could arise naturally from, relatively simple rules. And over the years, I think it's safe to say that these kind of ideas have permeated most subdisciplines of computer graphics. So this isn't an exhaustive list. Please don't get upset if your favorite area of graphics isn't on here. But if we look at some of the major sub areas of the field, things like geometry processing, rendering, fabrication, and animation, we see that large subsets of them are using ideas from computational physics. Physics-based animation, including fluids, physics-based character animation, and the control of those characters is sort of the obvious adopter of these ideas, but I'm always chuffed to see physics interpretations of algorithms in geometry processing, fabrication, and rendering. And I kind of believe that these ideas from physics disseminate for the reasons that they were originally attractive in animation, that complex behavior can emerge from simple rules. It's so prevalent now that I sort of think of large parts of graphics as a kind of computational physics, but one with very different motivation and vision than standard fields that dabble in this kind of thing. Graphics and the use of physics within graphics is special. And what makes it special is that whether we are talking about geometry, rendering, animation, simulation, or fabrication, we set this incredibly high bar in terms of complexity, fidelity, and performance. So graphics is almost like an extreme version of computational physics. And this is why I think you get so much incredible work coming out of the field. It's in reaching for this high bar we set for ourselves that we discover all sorts of magnificent bits of math, computer science, and really much, much more. And for someone who really loves to look at things through a physics lens, all of this is really exciting. But lately, I find myself looking back to that original Terzopoulos paper and asking how we're doing and living up to those original goals. And at least in my sort of little animation simulation corner of the world, this kind of visual computational mechanics community I'm part of, I think the answer is that, things could be better. And I submit that rather than make things easier, as we intended when we adopted this approach, we've kind of made them difficult, but in a different way. So I'm going to give you, my favorite example of this now. So in this example, here I am, I'm pressing down on a simulated shape with a force F. The shape is an elastic solid, and I've gone to Wikipedia and I've looked up the appropriate physical parameters to make this simulated object behave like it's made of a soft plastic. The simulated result kind of looks reasonable. The object is deflecting, and most of the deformation is happening in the thin part of the geometry. There's really only one problem here. It's a problem you can't see, but I've used a very, very high resolution simulation mesh, and that's very slow. And so, okay, fine, no problem. I'll do the whole thing again. I'll make the mesh coarser. It's going to be much faster. And if I do that, if I keep everything the same except the mesh resolution, the result of the simulation will be quite different. Now, keep in mind that the simulated material is the same, the applied force is the same, everything is the same except the number of little cubes that make up this mesh. Now, even if you're an expert in simulation, this is not what you'd expect from a class of algorithms that is aiming for sort of simplicity and to get things right in an emergent sense simply by correctly implementing the laws of physics. And actually, things get a lot worse once you start to consider contact between objects. So here we have a thin sheet of cloth sliding over the edge of a box. And if we represent this cloth using an unstructured mesh, we get these kind of ugly artifacts because our fake cloth can't bend where it needs to. And if we align the triangle mesh with the edge of the box, the fold looks great, but actually the cloth gets stuck since it can't actually slide around the edge. So, once again, this unexpected behavior occurs. And this is really weird because if you did all this in real life, the cloth would slide along the edge perfectly and it would look fantastic. And this really all ignores the fact that just to get to the point of making these mistakes, there's still the problem of generating the geometry in the first place. Even with really stellar and robust solutions like Tetwild, which I really want to stress is a miracle worker in terms of building volumetric tetrahedral meshes, we run into problems. So, if we aren't careful, we're going to get these unexpected failures. This kind of blobby character was modeled by my grad student, Ty. It's made out of NURBS, built in Autodesk Fusion 360, and we exported the surface triangulation, and we can generate a tetrahedral mesh because Tetwild is awesome. But, certain features like the collar have been irrevocably perturbed. And, if you were a designer, you might not expect this to happen. So what's the solution? What is the current solution to all of these issues? Well, the best thing we really have to solve a lot of these problems is just to let artists and graduate students kind of engage in a WWE style wrestling match with all possible parameters and variations of algorithms for these problems. And we do this in order to produce really beautiful results. And don't get me wrong, this works. We see the evidence of this in countless movies, video games, and yes, even graphics interface paper submissions. But all this is time consuming. And that's part of the reason you see the same meshes and tests over and over again. We sort of overfit the problems where we can assume this is possible because we want to amortize content creation effort. But arguably now, we actually need more expertise to rein in physics simulation since the effective parameters is often indirect. And so the game just sort of changed to focusing in on increasingly narrow use cases. And it moved away from the larger goal, which was to leverage a physics-based approach to generate diverse and emergent behavior quickly and easily. To be sure, there is lots of work being done by myself and others to try and remedy some of these issues. And so, what I'd like to do now is talk a little bit about some of that. So for instance, there are now a myriad of what we call numerical coarsening techniques to mitigate things like simulation mesh dependency. And these, when used in the right scenarios, can be extremely effective. They're so good, in fact, that you can use very coarse simulations to get results that not only look good, but match real-world outcomes in particularly challenging scenarios. So these 3D printed jumping mechanisms were in fact optimally designed using a coarsened simulation that is orders of magnitude faster than what we would have required to get the same accuracy without coarsening. Now, if you've seen me give a talk before, you've definitely seen this video because I just love showing it. The agreement between the simulation and the fabricated result is unbelievably good. It's every time I see it, I still can't believe it works so well. As an aside, this paper was actually rejected from the transactions on graphics before it was narrowly accepted to SIGGRAPH. So there's a bit of a lesson buried in all of this about stubbornly sticking with ideas that you have faith in, even if maybe others don't at first. And we've since refined the technique a little bit to work on a wider variety of mesh types in geometry. Here, the fine tetrahedral simulation mesh is an order of magnitude slower than our eigenfit method, but you can see that the results are almost identical. And my former master student, Honglin Chen, had another great follow-up to all of this with Alec Jacobson and Derek Liu that was much more general than our previous approaches, but focused on sort of geometry processing applications. The nice thing about this paper is that it had some notion of finding an optimal solution to this coarsening problem. All this work taken together is in service of mitigating the effect of mesh resolution as a hidden parameter and making the output of a physics simulation solely dependent on its physical parameters. This is not only great for someone like me who hates manually hunting around for parameter values, but I think broadens the use cases where physics-based animation can be applied. Interestingly, like numerical coarsening, our collision problem is also sort of a form of discretization failure. We've just learned that if you naively coarsen the simulation mesh to get more performance, you introduce an error in the material parameters. Well, it turns out that if you introduce this type of collision error, but if we introduce just the right degrees of freedom back into the system, these errors vanish. In our case, it turns out that the right degrees of freedom are the texture coordinates of each vertex. So, if you change the texture coordinates on a triangle mesh, you can make an image drift or move along on the mesh. And by letting the physics simulator itself control the drift and combine it with a bit of remeshing, we can solve this problem. And we get both this beautiful sharp crease and smooth sliding around the edges. We can even do previously impossible constraints like this sliding pup tent. So here, the string of the pup tent is represented by just a single line. And this example will immediately break on a standard cloth simulator. And we can even, poke this cloth with a bunch of spikes for some reason, and you can see it's happily sliding along unperturbed. We also capture some sort of nice detail like these buckling artifacts that make everything look a little bit more realistic. And this kind of comes for free just by fixing the discretization problem. However, even with fixes like these, we still have the problem of generating simulation geometry from some input representation. There are a couple of important questions on this front. One, what sort of input geometry should we be trying to convert? And two, what should our output format be? The most common form of input geometry in my field, at least, is a triangle mesh. So, we want to be able to convert triangle meshes to volumetric representations, but it doesn't necessarily have to be a tetrahedral mesh like the one pictured above. One potential alternative is what we call a cut cell mesh. And here we generate volumetric cells by clipping the input surface against a volumetric hexahedral grid. And if we're really careful about how we do this, we can robustly generate these cut cells for a wide variety of input geometries. So here's an example of using our robust cut cell generator called Mandolin on a subset of the Thingy 10K geometry dataset. And in the corresponding paper, we show it works on the whole dataset, as well as on meshes that are non-manifold, open, and self-intersecting. there's still a price to pay, and that the output of the volumetric cells are much more complicated than just tetrahedra. And we're still really working on the accompanying simulation technology. But this is so this is a preliminary airflow simulation run on a particularly ugly Jeep mesh. And I'll just say, watch this space, as there's more coming on this front that I'm very excited about. However, things like mandolin are only going to get you so far. What if you want to deal with models that aren't represented by triangle meshes? Something like this wheel, which has been designed as a NURBS model. Well, an alternative is to abandon explicit volumetric meshes altogether and use a mesh-free method. This method, which we call the shape matching element method, skips the volumetric mesh generation step entirely. And it requires only the input surface description, curved or not, to work, which makes it really, really fast to design things and then simulate it. So it's a lot of fun to play with. So this is really, really new work, and you'll be able to learn more about this at SIGGRAPH in the summer. So we have all these individual solutions to various issues with simulation, and they're all geared towards making things as simple and parameter-free as possible to let the physics shine through in the way it was originally intended. But the truth is, I'm still not sure how to put them all together. To be honest, I don't even know if all these puzzle pieces are even from the same box. What I really want for computational mechanics is kind of a general function that generates physically simulated output. It should consume arbitrary geometries and material descriptions and produce simulations. And that's a really big ask. But I have some confidence that it's possible. In areas like geometry processing, we're seeing good progress in building algorithms that provide obfuscated geometry queries. So for instance, winding numbers allow you to do inside-outside tests robustly on almost any input geometry format. For algorithms that require only this test, they don't need to care what input a user is providing. And that's definitely a step in the right direction. But I feel like in computational mechanics, we don't quite know where to go next. And we're just exploring. And the thing about exploring all this stuff is that it's slow. And that's partly why we take relatively small steps. Each experiment means building a simulation, and that's a difficult manual process. That's because there are not just computer science challenges to solve, but mathematical challenges and even experimental challenges. So the more I think about this, the more I feel like we have to turn this into this. So how do we do that? Well, the first thing to consider is geometry. Whether it's thin sheets, volumetric solids, fluids, triangles, NURBS surfaces, or particles, in simulation, the algorithm you use is heavily dependent on the form of your geometry. And this is a bit like, still having to program an assembly code. Ideally, we should be abstracting all of this away. So I'm pretty excited about meshless methods coupled with efficient sign distance representations to kind of completely hide all of this stuff from both researchers and users of physics simulations. For what it's worth, this combination of tools is starting to see some use in video games in order to simulate pretty large scale and pretty degenerate geometry, and the results are really promising. There are still a lot of open questions about how exactly to do all this stuff for highly deforming geometries with complicated material properties, but it feels like it's within reach. However, even if we solve the geometry problem, there are still even basic scientific questions about how we model complex materials. One of the reasons you tend to see the same sort of simulations over and over again in computer graphics papers is that we're still learning how to deal with all the material complexity inherent in the real world. There have been some previous attempts to automate this sort of measurements.
The UBC active measurement facility.
And then directly simulate results. And this is only going to get more important as we seek to broaden the range of output of physics-based methods. So, what's shown here is Dinesh Pai's Acme robot, which could automatically poke and prod an object to generate a simple virtual facsimile. And this is really like seeing the first camera that captures a truly physical object rather than just a 2D image or 3D scan. And just as computational photography has benefited from the miniaturization and proliferation of cameras for acquiring photographic data, I think we need to follow a similar path, but concentrate on capturing more of reality than just photons. And finally, I think we have a massive systems problem in the field. Unlike other fields like machine learning or even geometry processing, simulation doesn't have a widely accepted framework for easing the implementation of performant code. 33 years after the first paper in the field, we are still basically rolling our own stuff for each and every project. And you only need to look at the success of deep learning fueled by tools like TensorFlow and PyTorch to see how useful a community-wide engineering effort can be. So there's some hope. There are custom languages like Tai Chi, but there are still some real questions about how to get necessary technical features like automatic differentiation to play really nicely with the type of sparse data structures we typically encounter in computational mechanics. So full disclosure, I really started thinking about this after my daughter was born. I had a significant reduction in the amount of time I had for kind of esoteric C++ or GPU hacking. So this is really like a very self-serving goal, but I still feel it's the case of what's good for the goose is good for the gander. And so these are the problems I think are important to solve and the things that I think we need to build to solve them. And for me, this is all in service of kind of a great quest. And that quest is really to understand how the world works. And mechanics, especially as it's done in computer graphics, is a fun, satisfying, and useful lens through which to do that. But we have to be forever on guard of getting lost in the details. And here, I'm as guilty as anyone. As fun, useful, and intellectually satisfying as all this has been, the goal was never just to understand how some bunnies or penguins bounce down the stairs. The goal was to build and comprehend a world, and the world is much bigger and much more complex than any of that. So I just want to thank you all again for inviting me to speak, and I'm happy to take any questions now.
Okay, thank you so much, David, for the great presentation. Is there any question from the audience on YouTube that you want to ask David? Or from people in Zoom? Yeah, so David, you mentioned that you have you can actually work with different types of inputs. Like it can be nerves or meshes or something like that. And then you mentioned that for neural networks, we actually have made a lot of contribution. It's working very well, but here in simulation, maybe you are not working as well. So my question is for neural networks, for example, we have some agreement on the input. So the input should be a tensor, right? What is the right input for physics simulation?
Well, I think the right input is defined, by its interface. So in general, when you want to understand the physical properties of an object, the object itself is really a container. It's a blob of Euclidean space, and that blob has to be able to answer some questions for you. It needs to let you know if a point is inside or outside of the blob. It needs to let you know what are the material properties at that point in the blob. And so, in some sense, I don't really care how those query functions are implemented. I just want the interface. And I think, once we start thinking of things in terms of just having this interface, it becomes a lot cleaner. Essentially, this is like standard, this is like object-oriented programming, but for real life physical objects.
Yeah, pretty cool. So maybe the last question, because we need to go for the next presenter. So you probably know that Alec Jacobson is actually working to maybe use the latent vectors to represent the shapes, right? Only latent vectors that you can have a very compressed version of your model or shape. Do you think that the physics-based simulations that you have can be transferable to those types of representations?
So for us, in physics simulation and mechanics, things get very interesting when you have to consider deformation, because in the sort of things that happen on this side of the fence, it's not just enough to represent the object in a single state. We have to represent it in multiple states, right? We have to represent its change in shape over time. And this can get really complicated. Like if you consider, you know, a fluid, like if you go to Christopher Batty's webpage and you watch some of his amazing videos, you know, you can start with a bunny and it can turn into something completely different. There's shape change, there's topology change. And so it's unclear, you know, even if there is a compressed representation that can handle that with, you know, sufficient expressivity, right? I think it's a really wonderful idea, but it's this idea that there's no free lunch, right? If you compress your shape space, well, you better hope that everything that you've excluded is not actually needed to represent the proper behavior of the object. And it's, you know, I think it's going to be really fun to see, you know, how far we can push these things, where that all starts to break down.
Awesome. Thank you so much for the great presentation. And I'm going to give you applause, and you received a lot of virtual applause on YouTube as well.
Great. Thank you. It was wonderful to be here. Thank you.
Yeah, thanks so much.